In this segment, we're going to be talking about logistic regression. Logistic regression is going to be an alternative classification model to the perceptron, and it's going to be the foundation of a lot of the techniques that we build going forward in this course, including things like feed-forward neural networks. So logistic regression is what we call a discriminative probabilistic model. And what this means is that it places a distribution P of y given x over labels conditioned on input data points. So the alternative to this would be a generative model, which looks like placing a joint distribution over P of x, y, rather than a conditional distribution. For classification, this would include approaches like naive Bayes. We're going to come back to generative modeling later in this course, particularly when we talk about hidden Markov models. So for right now, we'll stick with this discriminative framework. OK, so let me write down the definition of binary logistic regression. So we are defining here the probability of the positive class, the probability that y equals +1, conditioned on the input data point. And it takes the following form. OK, so what you should notice is that we still have this dot product of the weight vector and the feature vector, which was characteristic of the perceptron algorithm as well. But now we've embedded it in this function e to the x over 1 plus e to the x. And so this is called the logistic function, which is where the name logistic regression comes from. And if we plot this for different values of x, what we get is the following. So this is y equals 1. This is y equals 0.5, and we get a kind of curve that looks like this. So it intersects the, at the origin, it takes the value of 0.5. You can confirm this, plug in x equals 0, you get a half. And then as it goes out in either direction, it approaches either +1 or 0. And so the main reason that this is useful is because it allows us to map from real, any real number into something that's going to be a valid probability. OK, so again, what this does is it takes this W transpose f of x quantity and turns it into a probability associated with the positive class. OK, and so we could think about the negative class probability. And without me writing it down, you should be able to figure out what this is. And the reason you should be able to figure that out is we have binary logistic regression. So P of y equals -1 and P of y equals +1 have to sum to 1. And so you can double check that the value that causes that to happen is this one. All right. And then the other thing we can ask ourselves is, what decision boundary does this imply? So remember, we're doing classification. So when I give you a point and you have a logistic regression classifier, you should be able to tell me a label for that point. OK, so one kind of plausible way of doing this is you return +1 if P of y equals +1 given x is greater than 0, right? So it turns out that this is equivalent to W transpose f of x is greater than 0. If that probability is greater than 0.5, we want to return +1. And that happens when W transpose f of x is greater than 0. And again, you can just look at what happens at the origin and kind of confirm that for yourself. OK, so basically the decision rule ends up being the same as for the perceptron. We're just comparing this dot product with 0, but now we have this kind of probabilistic interpretation. And so again, if you're just doing prediction, that doesn't matter. But where it impacts things is training. So how are we going to train logistic regression? So we're going to assume our labeled data set, which consists of points x and labels y. And we're going to have capital D of these. And what we want to do is we want to maximize the following quantity. Okay, so what we are maximizing here is what we call the likelihood or the discriminative likelihood of the data, meaning that we have a bunch of labels y for data points x, and we want to maximize the probability of observing this data. And so in this case, because we have a discriminative model, we're conditioning on x, and we're maximizing the product of the probability of each y given x. Essentially, let's set our model parameters w such that the data looks as likely as possible. And so we're going to write this as a maximization over w of, now we're going to transform this likelihood expression. Okay, so now this is the log likelihood because we've taken the logarithm. And so what you should be able to confirm for yourself is that, remember that log is a monotonic function. And so when we want to maximize the likelihood of something, or in general maximize any function, we can also maximize the log of that function. And as long as that function is going to be positive and the log is defined, the maximum remains the same. And so this is it's going to turn out that this simplifies things a lot for us kind of computationally to deal with log likelihoods. And so that's what we're going to do here. So we take this log and we can push it through the product and it becomes a sum, and then we get the max of a sum of log probabilities. And then the one more transformation we're going to do is we're just going to put in a negative sign and flip it around, and instead of maximizing the log likelihood, we're going to minimize the negative log likelihood. And the reason we're doing this is so that now we can think of this term as a loss in the sense of the basic machine learning principles we saw earlier. So we now have our training objective, which is negative log likelihood gets abbreviated to NLL, particularly in a lot of the deep learning frameworks. And now, in order to deal with this, and optimize it, we can call back to that framework that we introduced earlier of stochastic gradient descent. And in order to use stochastic gradient descent, what we need to be able to do is we need to be able to compute the gradient of each one of these terms of this outer sum. So the SGD loop involves picking, we're going to say right now one data point to deal with at a time out of our D, and compute the gradient of the loss on that data point. So that's a term that looks like this. All right, so remember that for the perceptron, we saw, just kind of defining this algorithm that, checked if you made a mistake and tried to kind of correct the value of the weight vector to make that mistake happen less in the future. Now instead, we've kind of formulated this first principles idea of maximizing the probability of the data, and now we're going to compute a gradient on this so we can try to directly optimize this objective function with gradient descent. Okay, so what we are going to do here is we are going to assume yi equals +1. So we're going to derive this for the case of a positively labeled example. It's a good exercise for you if you want to think about this more to try to work it out for a negatively labeled example as well. Okay, so what do we end up with? So we're going to plug in the value of the loss here, which remember was the negative log of the logistic function. So you end up with this. So again, the log kind of breaks up the division, and the numerator was this e to the w transpose f of x thing. The log also kills off the exponential, and then you negate it. And then in the denominator, we end up with this slightly ugly log of 1 plus e to the something, which cannot be broken up because we have this log of something, and you can't commute log past sum. Okay, so now we need to take the gradient of this expression with respect to w. So if you're not familiar with vector derivatives, again, you can just think about a dot product is just going to be a sum up for each term in w and each term in f of x of the product of them. And so when you take the gradient with respect to w, it's this linear sum, and the w terms just kind of go away and leave you with the f of x terms. All right. And then the second term gets a little bit more complicated. We need to appeal to the chain rule. So the way that log works is you get 1 over the kind of inside stuff of the log times the derivative of the inside. And so the derivative of exponential is exponential, again, times the derivative of the inside stuff using the chain rule, and we end up with this. Okay, and so now let's rewrite this a little bit. So we're going to factor out an f of x, and then we end up kind of cleaning up the second term here. All right, and so the second term is kind of cool now because we had this big mess of exponentials and 1 over 1 plus e to the whatever, and it turns out that we can simplify this now in the following way. Actually, I'll write it in this order. So this second term ends up just being the logistic function again. It kind of comes back out from the process of differentiation. And now we can just replace that with the probability of y equals +1 given x under the model. So this is a quantity that we kind of already have defined because this is the definition of our logistic regression model. And so we end up with something that we can kind of simplify in this way. OK, so then finally recall that the SGD update looks like this. You have to subtract off alpha times the gradient. So I'm going to write this as adding alpha times negative the gradient, and that gives us this. OK, so we did a whole lot of work, and recall that if we just look at this piece of it, we have something which looks very similar to the perceptron in the case of misclassifying a positive example. Remember, when we misclassify a positive example as negative, we have to boost up its score, and so we add in f of x to the weight vector. So here we have the same term, but this alpha times f of x is now modulated by this 1 minus p of y equals plus 1 thing. So then, like, just to kind of intuitively think about what happens, let's think about when this term is very close to 1. The model is essentially making the right prediction. We're not going to make much of an update because this second term, this 1 minus p of y plus 1 term, is going to be very close to 0 and sort of cancel out. What if instead this is very close to 0? Then we recover, again, like I was saying, the perceptron update, right? Because this 1 minus p of y equals plus 1 term essentially takes the value of 1 and the update looks basically like the perceptron update from before. All right, so what we're going to do in order to kind of understand this is we're going to let z equal w transpose f of x. And now we can rewrite the NLL, negative log likelihood, for this model as the following: log of 1 plus e to the z minus z. And so that's just following basically what's on the top of the slide here before we took the gradient. And what we can do now is we can plot this quantity z, or w transpose f of x, against the value of the loss. And so previously we saw that the perceptron had a kind of structure that looked like this. It basically, it has this sort of hinge-like behavior where it's 0, when the value of z is positive, when the prediction is correct, and otherwise it has this y equals kind of minus x sort of structure. And it turns out if you plot this thing, you end up with something that looks like this. And this is the loss for logistic regression. And what you should be able to convince yourself of is that, basically in the kind of limits as you go towards, basically this z term gets very large negative or very large positive, you end up with something very similar to the perceptron loss. And so the nice thing here is that these two algorithms, which were motivated from very different intuition, ended up doing almost exactly the same thing. So this kind of informs a little bit of how we're going to approach classification for the rest of this course. We're not going to be too concerned about whether we use perceptron or logistic regression or SVM. We're going to kind of stick with what ends up essentially being most convenient for us given what we're doing. So that kind of wraps up this segment about logistic regression and closes us off for basic binary classification.